Good morning, I'm Tang Jingyuan from the Hong Kong University of Science and Technology. The paper I will present today is the method on pose estimation of excavators based on onboard desk camera. The presentation includes the following 5 parts: motivation and background, objectives, methodology, experiment and result analysis, and conclusions. First, motivation and background. We all know that the excavators are very important and common heavy construction machines on construction site. Monitoring poses of an excavator is tightly related to the construction safety and automation construction. Previous study tracked the motions of an excavator using visual sensor with vivid location, like the digital camera or some surveillance camera set on site. Although they did develop a low-cost, user-friendly pose estimation system with good performance, there's still some problem like occlusion and limited field of view, which may make the whole system lose tracking target and fail to work. To address this problem, some common idea from a manned aerial vehicle, the UAV, can be referred to. To adapt to the dynamic environment, UAVs are equipped with an onboard navigation system, which is more flexible and reliable. But because the UAV is just an independent rigid body without multiple movable components, it cannot be applied to excavators for tracking multiple angles at the same time. So, the crucial issue need to be considered is how to develop an onboard pose estimation system for excavators based on visual sensors. So, our study aimed to design an onboard system for excavator using depth camera to address the challenges of frequent occlusion on construction sites. In addition, based on the proposed system, we should develop a partial pose estimation method to track the motion of excavated in 3D space. Let's see the workflow of our study. It could be divided into 2 major parts. Part 1 is about the hardware preparation, and Part 2 is about the pose estimation for excavators. Then let's proceed to some detail. The hardware preparation. In the first part, the desk camera installed on the cabin is simulated as the operator's eyes and estimate the poses of an excavator like human. And then a marker is attached to the lower part of this arm to mimic the focus of the operator's eyes to facilitate estimating poses. And then shown as this figure, we can get a similar view to the operators and avoid being occluded as much as possible. This is the first part of the methodology. Let's come to the second part of the methodology, the pose estimation for excavator. This part could be divided into 3 steps. Step 1, data collection and key point definition. In this step, the image data are collected using desk camera and the key points are defined, like the K1, K2, K3, to abstract the structure of the excavator. And then step 2, the single feature point tracking. In this step, the coordinate of the centroid of the marker in our study are tracked. Although the different kind of marker are allowed to be used in our method, our study used the monochromatics marker through extracting the color region and identifying the auto counter. We can find the centroid of the marker in this image and retravel its depth in a generated depth map. Combining the depth of the points and its location in this image, we can determine its 3D coordinates in the camera reference frame. Okay, and then we have the last step, the pose angle estimation of excavators. In this step, a geometric decoder is developed to estimate the pose angles, like these red angles, the three red angles, describing the motion of the boom and the arm based on the single feature points proposed in the last step and the physical parameter of the excavator. Here we show the geometric decoder for the excavator. It has two parts. In the first part, we should estimate the coordinates of the blind support like the K2, and then we will calculate the post angle based on the post triangles here, like this. So far, we can compute the trajectory of each post angle of the excavator to describe the motion of the arm, the boom, and the arm directly. And then we need to use the excavator to use an experiment to preliminarily verify the feasibility of the proposed method on a real construction site. About the experiment device, we use a real-life excavator and a desk camera like this. And then the camera was mounted on the bottom light of the cabin window like this, and the circular white marker was passed on the lower part of the arm like this. Okay. Although the three post angle can be computed simultaneously. We just select the drawn angle between the boom and arm, and the drawn angle between the boom and arm to evaluate. That's because this angle includes all the motion information and can represent the calculation based on the proposed method. And then for the experimental operations, we can see a work cycle start with a random initial pose and then go through the lifting and dropping back to the initial pose. And in each row, we have 210 independent measurements to be evaluated on the construction site. Okay, let's see the experimental result here. According to this figure, we can see a distinct cycle here corresponding to the motion of the arm, and the amplitude of these curves are consistent with the common operation of the excavator intuitively. And then from the perspective of the accuracy, we can see the root mean square, the RMSE, with the difference between the estimated result, the right one, and the ground truth, the black one, are 3.77 degrees here. Okay. And then we can see the deviation of our experimental results is lower than the average error of previous study or some related work in this area. So, and then we can infer the potential error source. This means this unstable estimation may be from the unavoidable slight displacement of the camera installed on the machine caused by the vibration of the machines here. In summary, we can get a conclusion from the experiment. The proposed partial post-estimation method based on onboard camera is feasible with real machines on the real construction site. And then at the end of my presentation, I would like to restate the conclusions. First, this study developed a partial post-estimation method for excavator using onboard camera. Second, the proposed method is feasible with a real machine on a real construction site with the average RMSE of 3.77 degrees here. Last point, the proposed method not only solved the problem of occlusion when using the visual sensor on site, but also provide a theoretical basis for the design of onboard motion analysis system for excavator. Okay, that's all. Thanks for listening.